So far we have talked about the failure mechanism of concrete in compression, what are the model that are available for concrete for normal strength as well as high strength concrete, and how the tension stiffening mechanism works. Usually, the structural elements are subjected to combinations of all these loads: axial loads, bending moment, shear force, and twisting moments. Okay, and here we looked at only this uniaxial compression, right? But you can also have biaxial compression that is shown here, or sometimes system can also be subjected to triaxial compression. So this is what we call that as if you have equal uh, compression on all sides, we call that as hydrostatic stress. Okay. Um, you must have studied in your advanced structural mechanics or strength of materials. Uh, uh, the state of stress at a point on an element can be expressed as an equivalent set of normal stresses, principal stresses acting in three normal directions. So, stress at a point, you know that in a Cartesian coordinate system, you will have sigma xx, sigma xy, sigma xz, similarly sigma yx, sigma yy. So you have nine stress at a point is expressed as a stress tensor. For a point, stress at a point can be converted into an equivalent set of normal stresses because it's easy for us to deal with in terms of principal stresses in acting in three orthogonal directions, right? So here, as we said, the loads can be combination of tension and compression also. So depending upon the type of load, the failure mode of concrete will change. Whether you have pure compression, pure tension, or biaxial compression or triaxial compression, your failure uh, mode is going to change. Okay. Now, what are the failure planes? Failure planes are nothing but the planes of maximum principal strains. Wherever you have maximum principal strain, tensile strain that are going to be there, those are the planes which are called as failure planes. Okay. Because concrete is weak in tension, usually the failure will be initiated by tension only, and the failure planes will be parallel to the loading direction in compression. So that's what, if you see, if you test a cube like this, then you end up this kind of crack. Okay, will be parallel to the loading direction. And in case of tension, when you are pulling in tension, we have seen that if you have element that is subjected to tension like this, right, the cracking is going to be like this. So the failure plane will be perpendicular to the loading direction in case of tension. Okay, so this is, you have to account for them in your design. Now we will discuss what is the effect of confinement under axial loads. Okay, so if you see here, we have plotted test results of cylinder which are subjected to different lateral confining stress. Okay, so you keep a cylinder and subjected to different lateral confining stress. Okay, or you can put it in a container, watertight container, and increase the water pressure, so through which we can generate this lateral confining stress. And for a constant lateral confining stress, if I keep increasing this uniaxial compression, we can get the stress strain curve behavior. Okay, so this is what we have it in this uh, graph, where in the y-axis we are plotting the axial stress, and in the x-axis we are plotting the strain. Just like what we measure strain, we have discussed in this uniaxial compression behavior. Same way, only thing is, along with this uniaxial compression, it is also subjected to some lateral confining stress. So this is a behavior, stress strain curve behavior for a concrete with a cylinder strength of 25 megapascal with no confining stress. That means the confining stress is zero. So you can see that this is basically is going to resemble the 25 megapascal stress strain curve that we have previously we discussed, right? It's going to reach a peak strain of about 0.002, and it is going to fail at about 0.004 or so. Now, if I start increasing this confining stress from 3.5, 7, 14, and 28, what you're putting it is, you're putting the cylinder under triaxial compression stress state. Whenever the material is subjected to triaxial compression stress state, through this lateral confining stress, what we are going to get is the strength is going to increase. For example, if I'm putting a 3.5 megapascal of lateral confining stress, 25 megapascal concrete, now the strength is increased almost up to 50 megapascal. And also what is doing is the failure strain also has increased dramatically. So this behavior keeps happening as I apply more and more lateral confining stress. I get increase in peak strength, and also I'm getting the strain at failure is going to be increased. In fact, in reinforced concrete column design in the module, we will talk about that. Precisely the role of the transverse reinforcement is to put the concrete core under this kind of triaxial compression stress state. So you generate confinement. With increase in this confinement, we can really increase the axial strength and the strain at which it is going to fail. So this is what the behavior. So that is what the role of the transverse reinforcement also. Now we have using this FRP, fiber reinforced polymer based confinement solutions for strengthening the existing column. There also exactly what we do is this: we wrap the column with these kind of fiber reinforced polymer sheet. When it is subjected to axial compression, depending upon the properties of this FRP system and the thickness of the layer and the elastic modulus of this FRP system, it is going to confine the concrete and putting it under lateral confining stress. So through which we can get very good strength improvement as well as ductility improvement. So that is the essence of this fiber reinforced polymer strengthening. That is exactly what it is being done by the transverse reinforcement also. So it is going to put the concrete core under compression. Now this increased strength can be denoted as F prime CC, which is a confined strength that can be related to this unconfined strength. For example, in this case, unconfined strength for the same cylinder will be 25 megapascal. That means when FL is 0, it is having 25 megapascal. That is what this F prime CO is. And uh, this is F prime CC is your, when it is subjected to lateral confinement, how much that peak strength is happening. Okay, Richard, uh, way back in 1928, he did all this testing of cylinders under different confinement stress. He proposes very simple and elegant equation which gives the confined strength as a function of your unconfined strength plus a function of your lateral confinement. So that means higher the lateral confinement that I'm able to generate, higher will be your confinement strength. Similarly, we can propose equation for what are the failure strain also. Okay, so higher the confinement strain, again you can see epsilon c is also increasing from 0.0035 to almost as high as 0.06. So you get this. Alright, so now we will talk about what happens for a concrete element that is subjected to biaxial load. Okay, we are not looking at three-dimensional state. You take a small planar element which is subjected to biaxial stresses. So I can subject this element either under biaxial tension, or I can subject it into biaxial compression like what we have here, or this is this element biaxial compression. So the element is subjected to compression on both orthogonal directions, or it can be subjected to one side compression, one side tension. So this is what we have it in this quadrant and this quadrant. Okay, as we've seen in the previous slide, when the element is subjected to lateral confining compression, the strength increases. So that is what it happens in this case. In both the directions, when you have compression, the strength at which it is going to fail is going to be increased by about 27%. It has been experimentally proven. So the biaxial compression is greater than what you get in uniaxial compression, and it increases by about 27%. If you look at this quadrant, both the stresses are tension. So when the concrete panel element is subjected to biaxial tension, we get nearly the same strength as the uniaxial tensile strength. And you know that uniaxial tensile strength roughly it varies from 8 to 15% of your compressive strength. There is no variation. Here you get increase because of the lateral confinement, but when it is subjected to biaxial tension, you get nearly the same strength as you get in your uniaxial tension. When it is subjected to combined axial compression and tension, in this case, if you see, in the horizontal direction, we have compression. In the vertical direction or in the orthogonal direction to that, we have tension. So, the presence of this tension, depending upon how much it is going to reduce your compressive strength. Okay, so that's what we have. This side is compression, this side is tension. So if you look at it, the strength, if I'm somewhere here, so you can see that the sigma 2 is some tension value and sigma 1 is some compression value. Higher the sigma 2, lower will be your compressive strength. That same behavior is observed in this quadrant also. Now only the directions of this compression tension has reversed. Now in the vertical direction I have compression, in the horizontal direction I have tension. Same way. So depending upon how much is the tension that I have, the compressive strength will keep reducing. For example, if I am taking at this level, compressive strength is lower than what you get in uniaxial compressive strength. Okay. So this is what the linearly it is going to increase. Now, concrete is not an even material, it is an uneven material. That means it is going to have different compression and tensile strength. Unlike metals like steel, you have nearly same strength in compression tension. Concrete is a quasi-brittle material and it is also called as an uneven material. It has different strength in compression and tension. For such kind of materials, we use failure theories like mole Coulomb failure to predict the behavior. Okay. So, in triaxial state, I think we have explained previously also, strength and ductility increases due to all around confinement of concrete. And this confinement reduces the tendency of the internal cracking because, as we have seen, that mechanism of failure for concrete cylinder and compression, seen that mortar crack will form, then mortar crack will start joining. So, first the bond cracks will form, then the bond cracks will extend, and then the mortar crack will form. Then bond cracks and mortar cracks will join together and it will reach a level of critical stress. After that, concrete will start dilating, right? But if you put this in confinement, it reduces the tendency of internal cracking and volume increase just prior to failure. So that is what happens in triaxial stress state. Now, for us to predict for a particular given stress state whether that element is able to withstand without failing. So here in a concrete, we define failure when it is undergoing fracture or when it is undergoing cracking. So failure criterion we have to develop. So failure criterion is basically it helps us to estimate the stress state at which the material reaches its ultimate strength. Okay. So we have different theories that have been developed. We do not have time to discuss all of them. You are most welcome to look at the classical textbooks, but these are the classical theories that have been proposed: maximum principal stress theory, maximum shear stress theory, maximum elastic strain theory, octahedral shearing stress theory, energy of distortion theory. And we also have for brittle materials like concrete, we have Moore Coulomb criterion and Drucker-Prager criterion. This Tresca and von Mises yield criteria, it is valid for ductile materials where the failure is initiated by plastic deformation that happens in the metals. If you look at in the principal stress place, for example, in sigma 1, sigma 2 plane, when you look at it for ductile materials like metals, actually the failure is governed by the shearing that happens. It's not from the normal volumetric expansion or compression. It is governed by the shearing deformation that is happening. Failure is governed by shear. So the failure criteria is actually independent of the amount of hydrostatic pressure. So the effect of hydrostatic pressure is neglected in these yield criteria. Okay, so you can see that this is the way that failure curve. The blue color, for example, is a von Mises failure criteria, which is widely used for metals. And also, what you have, this is a hexagon, that is a Tresca which is based on the maximum shear theory. Okay, these are the failure surfaces. The same thing when you look at it in three-dimensional stress space in sigma 1, sigma 2, and sigma 3, and if especially when you look at how it is going to look in the hydrostatic axis. Okay, so this actually, if you look at it, one mesus looks like a ellipse, and this looks like a hexagon with different sides. The same in the hydrostatic axis, when you look at this failure surfaces, it is going to, the Tresca yield surface is going to be like symmetrical hexagon, and one mesus failure surface is going to be like a cylinder running along this hydrostatic axis. What is hydrostatic axis? Where in this axis, sigma 1 will be equal to sigma 2 will be equal to sigma 3, where all these sigma 1, sigma 2, sigma 3 are principal stresses. Now, this failure surfaces or failure theories is valid for only metal or for ductile materials. However, for behavior of non-metallic materials such as concrete, soil, and rocks, they are not only characterized by the shearing deformation that are happening, it is also depending upon the hydrostatic pressure. Uh, there is a hydrostatic pressure dependence there. So you must have studied in your advanced structure mechanics. Again, the stress tensor can be converted into principal stresses, and your stress invariance also can be defined. So, or in other words, the failure uh, theories is also function of your stress invariant, which is I1. Now, as we have said, concrete is pressure dependent material. So the failure is not only function of shearing that is happening, it is also function of your hydrostatic stress component. So it is a pressure dependent material. So that is why the failure theories have to account for this influence of this hydrostatic stress component on the failure. So there are two theories that have been proposed. The first is the Moore-Coulomb criterion. It is also considered as a generalized version of Tresca failure. Again, Tresca failure we have seen, which is based on the maximum shear uh, there, but it is an extension of your Tresca criterion. And both these theories are based on the assumption that maximum shear stress causes failure. Okay, so in Moore-Coulomb criterion, what we are saying is it is not only a function of your shear stress, it is also a function of hydrostatic stress component. So here the failure criterion is defined by limiting shear stress in a plane which is assumed to be function of not only shear stress but is also function of normal stress in the same plane at a point. However, in Tresca criterion for ductile materials, it is assumed that this critical value of shear stress is constant, but here for brittle materials like concrete, we are saying that the shear stress tau, which is also function of your normal stress, okay, which is a Morse envelope curve. Similarly, Drucker-Prager criterion is also developed for brittle materials like concrete and soil. It is a 3D pressure dependent model for finding the failure of the material, and it is also again extension of all. It's also called as generalized version of this von Mises criterion. Okay, again it also is based on the assumption that octahedral shear stress at failure depends linearly on the octahedral normal stress and the through the material constants. It's not only based on only octahedral shear stress, it is also depends upon the octahedral normal stress, which is linked to through by material constants. So again here the failure occurs when the octahedral stress reaches a critical value. Now let's look at how this, for example, this Moore envelope curve can be derived. Okay. So as we have explained before, it considers failure as when the limiting shear stress in a plane to be function of normal stress in the same plane at a point. So if you see here, the failure of the material occur if the radius of the largest principal circle is tangent to this envelope curve. So now how do we find this envelope curve? So we can test material under different stress states. For example, I take a small, let's say Q, and I test it in uniaxial compression. Okay, so that's why we said, let's say we take a 25 megapascal concrete and we test it under uniaxial compression. Then sigma 3 0, sigma 1 is 25, you get this failure, more a circle for uniaxial compression. This is at failure. Okay, so when sigma 1 reaches 25, concrete fails. Similarly, I can also test it under, let's say, a cube under biaxial compression, where the major principal stress at failure is 83 megapascal, and the minimum compressive stress is 14 megapascal. So this is the stress combination at which it is again it's failing. So similarly, I can test at a larger stress with a higher compression of 129 and a lower compression of 28. So these are the different stress condition at which this concrete is failing. So what I do is I can develop now an envelope, because these are the different stress state at which the material is failing. So I can draw a tangent to this and develop this more failure envelope. This is the way we develop this more envelope failure curve. Now, in this again in a three-dimensional space, in principal stress space, if you look at it, this is the way the failure surface is going to look for more Coulomb and Drucker-Prager criteria. You can see that it is going to be like a cone for a Drucker-Prager, and again it is going to be like with a hexagon, and it is going to go and join and become a point in this thing. So this is the way it is going to look like. And if you look at it only in the deviatoric plane, and Drucker-Prager criterion is going to look like a circle, and this is going to be like this kind of a hexagon. So this is the way we define failure theories for concrete under combined stress state. Okay, so to summarize this module, in this module we discussed about different constituents of concrete, and we discussed the difference between high strength and normal strength concrete, and also what are the advantages of using lightweight concrete. We briefly discussed about chemical composition, what are the hydration process, and what are the reactants, how fast different reactants are reacting. And we also in detail we discussed how the failure is going to be under compression, how do you test concrete under tension and establish different constitutive relationship. And there is also going to be size effect and platent effect on concrete strength. We talked about that. And what is characteristic strength of concrete in compression, which is a very important design parameter. That also we talked about. And we also talked about what is tension stiffening. Okay, what is the effect of tension stiffening on the response of structural element. We briefly discussed. And behavior of concrete under multi-axial stress state was also discussed. And finally, we also presented different couple of failure theories, right? More Coulomb as well as failure theories for concrete under combined stress state was also presented, right? All right, so these are some of the references that we have used for making this material. And so with that, thank you. We'll end this first module for this materials with this, and we'll continue with the other two modules in the subsequent lectures. Thank you.